Okay, so we're gonna do the neural evolution now. So we're gonna need the library. So I'll put a link to this in the description as well. So first thing we need is the matrix. Let's get raw, and we'll copy this, make a new text file, call it matrix.java. If I want to change it, and then let's just open it with VS Code. Whoops. Close all this. Okay, so file, save this, and then okay, let's go back and grab the neural network. So you can open up demo and then make a new tab, call it neural network, and get the raw. So we'll copy this in and save that. Okay, so now we've got our library. Let's just run it. Seems good. Okay, we're not getting errors, so let's start with the player. Okay, so now we'll do we'll do the neural network. Firstly, we just want to comment out jump. So we're not jumping anymore. It's gone. We're not the jumper. Now, instead of having one player, we can have players. Then we'll also do a final int total players, and let's have 100. So let's grab a for loop and give ourselves some space, and then this will be players, and then we'll grab this and do players that add a new player. And then I'm also going to do a bit of alpha. So let's just see here. Where's add new player? The method demo enemy. Okay. So we just need to, of course, make this a player. Okay, so our update and show also needs to change. So we'll grab that, and then to show, we'll just do the same, but having it show. Okay, our collision. Okay, for collision, we'll also need to do the same. So grab a loop here, and then I'll say players that get I, of course. So players that get I, players that get I, players that get I. And then we'll format for instance, if players are not collision, players dot has collided, else players hasn't collided. For size, players show. Why wouldn't there be players? Oh, okay. Of course, we want to add the total players. So there we go. So now all 100 are sitting here. So we need basically a function to have the player be able to make decisions. So we'll call it decision. And then we're going to need inputs so that we can give information to the player. So we kind of need this to be things that the player will find useful. So inputs equals a new float, and I don't know the size yet, so let's leave this. Okay, so now we want to get the closest enemy again. So I'm just going to copy this, and this will always give us the closest enemy. So let's start by defining the inputs. So for 0, let's say we've got, our x position, which we will normalize to between -1 and 1. So for inputs 1, we'll then have our y also normalized. We'll have velocity, and let's just normalize it by some number. Then so we've got so we'll have our width and divided by width. Then we'll get a height and also normalize it. Okay, so that's basically information relevant to the player about the player itself. So now I'm going to copy this, and let's make this 5, 6, 7, 8, and 9. And then let's grab our closest enemy and give it information as well. Closest enemy has the speed, and then also got a width, also got a height. So now we know that our float is 10. So the next thing we want to do is give the player a brain. So we're going to do an overloaded constructor. So we copied the first one, pasting it in. So now we want the player to be able to receive a brain, and then if it does, we'll just say brain equals b.copy. So this is when we provide a brain. So for example, from Gen 1 to Generation 2, a brain will be provided. So now we need to make the brain. So it'll be a neural network, and okay, that's neural to brain, and then brain will then equal a new neural network. We know we've got 10 inputs, so we're putting 10. Then we need a hidden layer or size, and then output. So if you think about outputs, what can a player do? It can either jump or not jump. So let's say 2. Then for the hidden layer, it's a good idea in practice to have it between your input size and output size. So in this case, it's 10 and 2. So 10 plus 2 is 12, and somewhere between there, let's say 6. So now let's go back to our decision function. And now we want the player to be able to actually take the inputs, make a guess, and then give an output or an array of outputs. So it will either jump or not jump, or depending on how many outputs you have. So, okay, let's make outputs, and then we'll do brain dot feed forward, which is a function of the neural network, and we'll give it the inputs. Okay, so now we'll say if, for example, the first output is greater than 0.8. So so in this case, this is for jumping. So we want to be very sure that we're going to jump. So that's why I'm putting it to 0.8. And of course, we want to check the Boolean if we're grounded. So only if it wants to jump and can jump, then jump will occur. So then we just say jump, right? So else, so this would be smaller or equal to 0.8. We then would have, for example, this again, but this time our second output. But since there is literally nothing it can do, we'll just leave it like this. So now we have this function. Let's just rename it to something different, think, and go where we're updating and just say think. So now, let me just see here, forgot a semicolon, and we just check there, typo, it should be a capital F, closest enemy, so let's just see. Let's, for now, just start our enemy on screen, maybe. So minus the width. Can find the closest enemy. So let's just see here. Null pointer 0, 1, 2, 3, 4, 5, 6, 9. Null pointer exceptions. So okay, let's see if it actually found the closest enemy. So let's just check this. No, it did not. So okay, for now we'll just say let's see, if the closest distance and the enemies dot get I dot top right dot x is greater than x. Okay, for now we'll just get rid of this, and then of course there's no enemy here, so let's see, enemies that add. Why would it not find an enemy? Float, infinite, okay. Enemy class is null for entire enemies size. Let's just say if enemies.getI.x is greater than x. This work. And okay, see here. So no enemy has been pushed yet, which is a problem. So let's just say we want to push them earlier. And again, at this point, no enemies were pushed. So let's go back here. Push another. If int I is smaller than enemy size, minus 200. Why are you not pushing more enemies? Yeah. Okay, so a problem now is that we're not adding more enemies. So let's just see if it actually gets here. Print line test. So this isn't happening. So I'm just going to move this here. And let's just say is if the enemy's x is smaller than width divided by 2. So there it gets added. And then smaller equal. Now it's just adding a ton. Why wouldn't that work? So okay, let's move this back and okay, let's say if the enemy size is greater than 0, let's do float w, which it would be width divided by 2, and then if enemies dot get let's do enemies dot get the enemies dot size minus 1. So the first enemy. So 1, 2, 3, 1, 2, 3. Okay, if that's smaller than w, then let's add another enemy. So enemies dot add a new enemy. Let's see here if enemies. Let's just do that. And the operator, when done, enemy float. Oh, of course. So just give it a actual float, and then let's see here. Okay, so new enemies are now appearing, which is good. Now we'll say something like 100 or I don't know. Let's just see how quickly it adds. That's very quickly. So maybe minus 200. Yeah. So now this shouldn't be null anymore. And yeah, there we go. So let's just make sure we're checking for in front, and let's make this top right. So we know we're checking for any enemy in front of the player. So what did I get wrong? Null pointer exception. Okay. Apparently not. It's fine. But now you can see the players are actually making decisions. Now, we don't know, and they don't know, if the decisions they're making are actually good decisions. So now, a way we can use nature and genetics is we can say, okay, any enemy or any player that goes further, so for the time that a player is alive, we'll add a score. So in the player update, we now need to define the scores. So let's make a score, and then set it to 0, and we'll also give it a fitness. And then in update, since it's alive, the score gets updated. So there we go. So now let's just take this out, and we're going to comment this out. So let's see here. Okay, the players are jumping. That's good. Okay, so now when a collision happens, which is here, we want to remove that player. So we'll say players dot get players dot remove that player. So and then this will just comment out, and then one remain there, they're gone. Okay, cool. So now we're gonna go to the next generation of players. So okay, what we're gonna do now is just grab the next generation, which we'll do by saying if this player size equals to 0, then we're gonna go take me to the next gen. Okay, so in the next part, I think we'll do the genetic algorithm and then basically wrap up. So, okay.